playlist together, and we realized we didn't have a lot of songs in common. So naturally, we wanted to use Bayes to determine if we both liked the song. By far, the most challenging part was getting the data because there's like no data set catered to Ava and I on the internet. So we labeled all the data by hand. We wanted to categorize a song into like yay, which meant we like the song, or nay, which meant we don't like the song, and that's here. And every row is a song. Each song has like an artist, a genre, year, beats per minute, and all other features.
The two types of Bayes classifiers we use for multinomial and Gaussian. So for multinomial, I think this works best with like categorical data. So for our data set, this would be artist, genre, and year. I think technically we could do like Gaussian for year, but because the range of years is so small, it'd be like better in this case to treat it as multinomial. And then this is like the formula that we like learned in class. So the posterior probability is like the probability that we're trying to get. PC, or like the class prior probability, would just be like probability of a song being yay or nay. And then likelihood, I think that's like the conditional probability. So like the probability of like an artist or genre or year being yay. And then PX is just probability of artist.
And then we use Gaussian for numerical data like beats per minute, energy, danceability, and other spawned by API. So this is the Gaussian formula. In a nutshell, you plug in the number, let's say it's beats per minute, and then the sigmoid is standard deviation, and then mu up here is mean, and then it outputs the likelihood of x given a class. This is the code we use for Gaussian. So the input, so we have two functions for Gaussian. One for the likelihood of a song in yay, and another for the likelihood of a song in nay. The input is the row, because earlier we explained that every row is a different song. And the x value in this formula is just, in this case, the specific beats per minute. And the output of the function is the output of the formula, which is the likelihood. This just shows that this variable is the mean of all beats per minute. This is the standard deviation. This is also the standard deviation. This slide explains that for the other
So this is for artists. So over here, we get variables, artist yay data and artist nay data. So what this basically does is it filters like the training data frame, which is titled DF, and it should only be selecting rows that are labeled yay or nay for this one under the artist column. So like this part, this just gets all the rows that are labeled yay, and then like artist at the end gets it so that it's only dealing with the artist column. Yeah. And then list of artists, we just wanted to get the list of like all the unique artist names. So DF artist, that just gets all the like elements in the artist column, or like the total list of the artist names. And then we converted it to a set to remove any duplicate names. So there's just like one of each artist. And then we converted it back to a list. And then like non-artists, it's just to find the length of the list of artists list to get the number of unique artists. Okay. And then artist yay count, that's just to count how many times an artist appears in artist yay data, or like how many days a particular artist has. And then so we used the dot value counts, which is a pandas method, and it's used to count the occurrences unique values like within a panda series. So if you like printed out these two, you would get something that looks like this. So the artist and then the number of yays or the number of nays the artist has. And then artist yay F, that's just an empty dictionary to hold the probabilities for yay songs. So the key value pairs in the dictionary would be artist as the key and then the probability of it being yay. Okay, and then down here, here. Okay, yeah, so for artist and list of artists, this basically just loops over each unique artist in the list of artist list, and it iterates like through all the artists in the list and then assigns a yay or nay probability to each one. And then over here, this part, that just gets the counts of artists in all the yay songs, and if the artist is not in list of artists, then it just assigns like the numerator, like this part, to 0. And then to account for a 0 probability, we just added 1 to the numerator. And then this basically just like updates the dictionary over there, with artist being the key and the probability being the value.
So at first, when we used all the features, we had an accuracy of 61%. It's not too good. That's because we realized a lot of the numerical data, like beats per minute, the stuff we use for Gaussian, Ava and I don't really care about that. So when we say we like a song, it has no correlation with those things. However, individually, artist and genre and year had like a higher accuracy rate. You can see that artist had an accuracy rate of 78%. Genre and year both had an accuracy of around 60%. So then in the final probability, we just used only artist and year, and that yielded us an accuracy of 82%.
Okay, and some possible improvements for our model. One would definitely need to get more data. So because we like labeled the songs we like and songs we didn't like by hand, we only had around like 750 rows. And for reference, like the Spanish hand assignment that we did in class had around 6,000 rows. So we do think that if we had more data, then it would just yield a higher accuracy. And then we could also consider like other applications of music. So like Claire said, we don't really care about BPM, danceability, and energy in our music. We kind of just listen to it like for casual enjoyment. But for like event-specific playlists, like for running or dance parties or stuff like that, those like Gaussian, the Gaussian columns, like danceability and stuff, would probably be really good.
That's all. Thank you.